Hello and welcome back. We are very glad to see you, and big thanks to all of you who have subscribed to our channel since our last video. Today's video will be a sort of continuation from our last video dedicated to RC filters. Today we are going to focus on high-pass RC filters. Primarily we will define what is it that we are amplifying and filtering. And at the end we will show a full PSpice simulation of high-pass RC filter. So, let's get on with today's video. If you enjoy practical electronics tutorials like this one, please subscribe to the channel. Don't forget to like the video and enable notifications so you don't miss future projects. Thank you. In almost all of the tutorials dedicated to amplifiers there is no mention of the signal at all. Myriads of videos and written tutorials dedicated to amplifiers, and almost not a single one of them, explains what is exactly that we are supposed to amplify, and what is the origin of the signal we are amplifying. Shocking. And if you are new to the world of electronics or just trying to learn, you will often see a picture of simple sine wave, representing only God knows what. No markings, no coordinate system, no amplitude, no period, nothing, just a squiggly line, all alone in the world. And we are supposed to know what to do with this out of our collective butts. Now, let's dispatch with this stupidity once and for all, and define where does the signal comes from, why are we amplifying it, and why is it always sine wave in every tutorial. The origin of the signal. First, amplifiers were invented to amplify audio signal. We have full video dedicated to this topic, so if you are interested to learn more, go and check it out. It is episode 9 of this season. Logical question is, where does audio signal comes from? The microphone. Still today, the simple microphone is one of the most common ways to generate and record audio signals, whether that being human speech, music, or something else. There are several ways that microphone converts sound into electrical signal, but what is common for all types of microphones is that it always contains some sort of membrane that oscillates under the pressure of sound waves, and then that oscillation gets converted into electrical signal. Do not mix sound with audio signal. The first one is mechanical pressure wave that travels through the air, and causes it to oscillate. Audio signal is electrical representation of that pressure wave, generated by the microphone. Simply put, microphone converts sound, that is the mechanical wave, into corresponding electrical signal. You can already guess that speaker does the opposite thing to the microphone. It converts electrical signal into sound wave, that we can hear and listen. To summarize, in almost all instances the microphone is what generates original audio signal that we are later going to amplify and process. Simple enough. Now, with that out of the way, let's deal with next stupidity. Why is it always the sine wave? Imagine a note, let's say F3. In order for some music instrument to produce this exact note, the instrument must generate sound wave with exactly 174.614 Hz frequency. That is F3 note for you. Now, let's go 2 octaves higher and play note F5. Again, in order for some music instrument to produce this exact note, the instrument must generate sound wave with exactly 698.456 Hz frequency. That is F5 note for you. In both cases, we have visually represented sound wave with corresponding sine wave. Now, imagine psalm with thousands of notes, some of them playing simultaneously, with lot of different instruments playing different notes. Some of these sound waves will interfere with each other, in constructive or destructive way. This is one of the basic principles of wave theory, constructive and destructive wave interference. So, as a result, we will get what we visually represented as audio signal, shape with lots of peaks of different amplitude. All these peaks are amplitude of different sine waves, added together, representing different notes, that have interfered constructively or destructively. If you have ever used any audio processing software, you are very well familiar with this shape. And now, you know how it's made. Now, using visual representation of an audio signal, like the one on the screen, is very confusing, especially for those who are new to all of this gobbledygook. Sound waves interfering constructively or destructively, amplitudes, frequencies, periods, peaks and God knows what else, can be very confusing. In order to simplify visual representation of an audio signal, we choose a simple sine wave to represent entirety of the audio signal. This is why it is always this stupid picture of sine wave. Just for visual simplicity, and that is all. No one is preventing you to use square, triangle or saw wave, as a visual representation of an audio signal. Representation of an entire audio signal, with simple sine wave has become common practice, nothing else, nothing more. Now, when dealing with amplifiers, RC circuits, or in case of today's video, high-pass RC filters, this simple sine wave represents one, many and all of the frequencies. If we want to emphasize that we are dealing with single frequency, or a range, we have to put a note, otherwise, simple sine wave represents every frequency, or entirety of an audio signal. Let's get back to RC filters. If you are interested to learn more about this topic, we strongly encourage you to watch previous video, episode 25. There you will find all necessary theory about RC circuits and filters. For those who are new, a quick reminder, high-pass RC filter is electronic circuit, containing a capacitor and a resistor in series, where resistor is connected to the ground with one terminal. Its function is to eliminate undesired frequencies from AC audio signal. Its main parameter is cutoff frequency. Everything below cutoff frequency gets attenuated, while the rest of the signal goes unchanged. One common real-life implementation of this circuit is dividing audio signal for playback on subwoofer and stereo speakers. If you have watched our previous videos, you are very well familiar with this circuit. It is basic NPN transistor amplifier circuit. As you can see, the capacitor and resistor are two, visually create high-pass RC filter. Also, from previous video, we have learned that simplified impedance that AC signal sees, consist of resistor R1 and R2 in parallel. There is a full explanation of this entire calculation in previous video. It is kinda prerequisite to fully understanding this video, so please go and watch it. Our job today is to define values for all components in the circuit, create simulation circuit in PSpice software and do frequency sweep analysis, so that we can observe output from our amplifier, depending on frequency of an input signal. So, let's get to it. From previous video we have learned that what AC signal sees in terms of input impedance, is combination of resistors R1 and R2 in parallel, all that in parallel with current limiting resistor Re who is in series with internal equivalency base emitter resistor small re. Plugging all the values for all resistors we get that for cutoff frequency of 300 Hz we need 0.6 microfarad capacitor, with equivalency input impedance calculated at 900 ohms. Let's redraw this circuit with new calculated values. We will use built-in AC signal generator in our simulation software. Please take close attention to definition of AC source parameters. They are as follows. V off is DC voltage offset of an AC input signal. We will set this to 0, because we do not want any DC offset. Next parameter, V amplitude is the amplitude of our input signal. We will set this to 0.5 volts, as our input signal has 1 volt point-to-point value. Next is frequency of our signal. Set it to any value, it is not important, because in simulation frequency sweep, this parameter will take every possible value from 1 to 10,000 Hz. And last parameter, AC, set it to exact value as V amplitude, because frequency sweep simulation requires this parameter to be set to exact value as V amplitude parameter. So, set it to 0.5, since that is 1/2 of our 1 volt point-to-point input signal. Remember that amplitude of the signal is half of its point-to-point value. Resistor R equivalency is calculated to be 900 ohms, and capacitor C is 0.6 microfarads. Now, let's go into our simulation software and create circuit. First, we will place resistor and capacitor into series. We will connect all components with wires. Next, we will assign them proper values. Next, we will insert AC input source, define its parameters, and tidy up schematics a little. The process is pretty self-explanatory, so you will not have any problems recreating this circuit in any simulation software. We will create new simulation, give it a name and save it under working folder. Next, from analysis type drop box we will choose AC sweep simulation. Under AC sweep type we will choose linear scale, define start and end frequency, along with total points for simulation to capture. Since we have created new simulation, we will have to add probes again into our main circuit. Now, let's run simulation. Let's maximize working space by closing unnecessary windows, and let's rescale graph by redefining y-axis to 750 mV, so that we can see top of our graph unobstructed. Let's add to our graph a horizontal line, at exactly 0.5 volts, which is peak of our signal amplitude. Let's bring into focus our simulation output and let's analyze what we did. First, we opted for AC sweep type simulation. This type of simulation cycles through all defined frequencies, in our case from 1 to 10,000 Hz, and measure output from circuit for each and every frequency in that range. Instead of manually changing frequency parameter for our AC input source, this type of analysis gives us the opportunity to automatically cycle through all frequencies. This is why the frequency parameter for our AC input source is irrelevant, it can be set for any value when this type of analysis is in work. Next, the probes measure amplitude of output signal. We have positioned probes so that they take reading from equivalency resistor, which is analogous to the signal that would appear at base terminal for our NPN amplifier circuit. Now, let's add another line, this time a vertical one, at exactly 300 Hz point at x-axis. This will mark our cutoff frequency. The function of our high-pass RC filter is to filter out all frequencies below 300 Hz and attenuate them, or simply put, to shrink their amplitude, and for all frequencies above 300 Hz, to let the signal pass unchanged. Left of our orange vertical line, that marks 300 Hz cutoff frequency, we see that signal amplitude slopes towards 0 volts. Analogous to that, everything to the right of our orange vertical line, passes through the circuit almost unchanged. Now, let's remember from our previous video that there are no ideal electrical components and circuits, so is the case with RC filters. There is always some loss, some voltage drop and some interference. These imperfections manifest themselves in this slope that we see in our output signal. If this was theoretically ideal scenario, output from RC filter circuit would not have any slope, it would be square line. Who knew that learning about and running simulation on high-pass RC filters could be this much fun? Now, let's see what happens when we take real NPN amplifier circuit, plug in all values for capacitor and resistors and run the simulation again. Let's recreate simulation based on this circuit from our previous videos. From Place menu and PSpice component submenu, we will choose and place all of required components, power source, AC signal source, make necessary connection between them and define values for each individual component and power source. The process is pretty self-explanatory, so enjoy the animation. For analysis type this time we will choose time domain with duration of 1 second. We have previously set AC signal frequency parameter to be 10 Hz. Let's place our probes at collector terminal output and ground, and let's run the simulation. We will close all unnecessary output simulation windows and rescale y-axis to display values of signal from 0 to 5 volts, so that we can see our signal in proper scale. Now, let's analyze the output. Our output signal swings around 3 volts, which is exactly what we wanted to achieve. However, there is no amplification. So, our high-pass RC filter has successfully attenuated input AC signal with 10 Hz frequency, so there is no amplification of the signal. Now, let's see what happens when we change frequency of input signal to 1000 Hz. Let's redesign our simulation circuit and also, let's rescale simulation duration to 10 milliseconds, increase resolution of the simulation by setting maximum step size option to 0.01 millisecond, and observe the output from the simulation. Let's close all unnecessary simulation output windows, and rescale y-axis from 0 to 5 volts so that we can see entirety of our output signal in proper scale. Now, isn't this a thing of a beauty? Our signal comes out almost in its full amplification. Even if we have set our cutoff frequency to 300 Hz, due to imperfections of RC circuits, even signal with 1000 Hz frequency will be slightly attenuated, but not by much. This is totally acceptable output. If you want, you can plug in different values for AC signal frequency and observe the output. Just don't forget to scale both X and Y axis in order to get proper and true scale for signal display. We have enjoyed immensely making this video and presenting to you how to simulate high-pass RC filter and NPN amplifier circuit using PSpice software. If you have any questions, please leave them in comment section, we will be more than happy to answer them. Please, before you leave, show your appreciation by liking this video, leaving a comment, sharing it, and please subscribe to the channel. Thank you, and see you next time. Bye.